Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing ISIS concepts, configuration, and monitoring in Junos. In this lesson, we'll be covering the IS PDUs. In a previous lesson, we discussed that the fundamental building blocks for the exchange of reachability information for ISIS is the PDU, or Protocol Data Unit. The PDU is a similar concept to the message types of OSPF. So, let's first do a quick rundown of the PDU types that ISIS uses. Here, we see that there are 4 different types of PDUs. The ISIS Hello, or IIH PDU, the Link State PDU, or LSP, the Complete Sequence Number PDU, or CSNP, and the Partial Sequence Number PDU, or PSNP. We'll be reviewing the data contained and the format of each of these PDUs in detail in this lesson. Though here, we can see a high-level description of the purpose of each of these PDU types. The IIH PDU is much like the OSPF Hello, in that it's used to discover neighboring routers, or intermediate systems, as they're called in ISIS. The Link State PDU is used to transmit link state information between ISIS speakers. This is very similar to the OSPF LSU packet, where this PDU contains individual TLVs, which contain the reachability information for each. These TLVs are akin to the OSPF LSAs contained within the LSU. Moving down, we have the CSNP. These packets provide a complete description of the LSDB of the local router. These are used and exchanged to see what LSPs are missing from one another's LSDB. This is a very similar function to the DBD, or Database Descriptor packet, seen in OSPF. It's worth noting that a DR, or designated router, on a broadcast segment will send back CSNP packets as an acknowledgement for the receipt of LSPs. And finally, we have the PSNPs, which are used to request certain LSPs from a neighbor. When a router sees the CSNP of the neighbor and determines it is missing some LSPs listed in the CSNP, then it will send PSNPs back to request the missing LSPs. Now, we've mentioned the usage of type length value fields, or TLVs, in ISIS a few times. Let's take a closer look at the type of TLVs that are available and how they're used. All information exchanged between ISIS speaking routers are contained in TLVs. This is because it's an easy way to transmit information. Where the type field defines what type of information is in the payload of the data unit, the length field tells the receiver how long the TLV is, and the value simply contains the payload or data of the TLV. There are many types defined for ISIS. Some of them are shown in this table. This is not an exhaustive list, though contains many of the type codes for TLVs we would encounter in our networks. Note that since the IPv4 routing extensions were not added to ISIS until later in the protocol's life, the TLV codes for IPv4 reachability information are down here at the bottom, starting at type code 128. When it comes to studying for the exam, I recommend knowing at least the usage for TLV type code 1, 10, and the IPv4 extension type codes down here, as these are likely to appear as a question on your exam. Now that we have a sense of the information that can be contained in a TLV and how they're structured, let's dive deep into each of the PDU types, starting off with the IIH PDU. The ISIS Hello PDU, or IIH PDU, is used just like the OSPF Hello packet to discover neighboring ISIS speakers and determine the level of their adjacency if a neighbor is discovered. Even after an adjacency is formed, IIH PDUs are still exchanged at a regular hello interval and used as a keep alive mechanism. We did mention that the IIH PDU determines the level of the adjacency if a neighbor is discovered, the level 1 or level 2. The frame formats of the level 1 and level 2 IIH PDU are identical, though level 1 IIH PDUs are destined for this MAC address, and level 2 to this MAC address. Another term we'll need to be familiar with is DIS, or Designated Intermediate System. This is simply a DR and performs the same function as the designated router in OSPF, though is called a DIS instead. A DIS will originate IIH PDUs every 3 seconds, though non-DIS will only originate an IIH PDU every 9 seconds. Within the IIH PDU, among other information, we'll review in the next slide, the originating IS includes a list of all neighbors known to the originating IS. This is how ISIS forms neighbor adjacencies, is it will look for its own identifier in the list of neighboring ISs of a received IIH PDU, to know that the neighbor router has received its own IIH PDU. Now, let's take a closer look at the fields of an IIH PDU and the information contained. Here, we have the 6 fields of an IIH PDU. The circuit type simply specifies whether the originating IS is able to form level 1, level 2, or both level 1 and level 2 adjacencies. The source ID simply contains the system ID of the originating router. The system ID is similar to the router ID in OSPF, a unique identifier for the local device which is not duplicated anywhere in the autonomous system. Then we have the holding time, which is the same concept as the dead interval in OSPF. This defines the amount of time the originating router will wait between receiving IIH PDUs from a neighboring router before declaring the router dead. The PDU length field simply specifies the number of octets long that the PDU is. The priority is used for the election of a DIS and can be a value between 0 and 127. Finally, the LAN ID includes the system ID for the DIS of the broadcast segment. There's another octet to differentiate this LAN ID from another that the DIS may also be designated for. Let's now take a look at the bit field format of the IIH PDU. As we mentioned in a previous slide, there is a different IIH PDU depending on whether the link the originating router is transmitting the PDU on is a broadcast link or a point-to-point link. On the left here, we have the frame format of a point-to-point IIH PDU, and on the right, the broadcast format. The only difference is towards the bottom, where the broadcast IIH PDU includes a reserved bit, priority field, and the LAN ID for the broadcast segment. The first 8 octets of the PDU is the standard IS IS PDU header information. These octets are present in each type of PDU we'll review today. When it comes to studying for the exam, you do not need to memorize the PDU frame formats. I generally feel having a familiarity with the bit-level detail of the information that's exchanged in dynamic network protocols is beneficial for understanding how the protocol works. Let's move on to our next PDU type, the link state PDU, or LSP. The LSPs in ISIS describe prefixes that are reachable from the local IS and describe the adjacencies. LSPs are periodically flooded throughout an area to ensure the information in the LSDBs of the routers in the area does not become stale. The three events shown here can also trigger LSPs to be flooded. When a directly connected link to a neighbor goes down, an LSP is flooded to describe the loss of connectivity. When a new neighbor adjacency is formed, LSPs are flooded to describe the new connectivity. And when the cost to an existing neighbor changes, LSPs are flooded to update the LSDBs of the ISs in the autonomous system. A differentiating field is used to separate Level 1 LSPs from Level 2 LSPs. So, let's take a look at the bit field format of the link state PDU. As with the IIH PDU, the first 8 octets shown here are the IS IS PDU common header fields present in every PDU. As we see in the LSP, though, the information transmitted includes the remaining lifetime of the PDU before it should be aged out, an identifier for the LSP, and then sequence numbers, which describe the reachability information, and a 16-bit checksum to validate the data is uncorrupted. The LSP ID field is what is used to distinctly identify this LSP, so that it may be requested in a PSNP or included in a CSNP. Let's now move on to the CSNP for more detail there. The CSNP, or Complete Sequence Number PDU, is very similar to the DBD packet of OSPF. The CSNP contains a complete list of all LSP IDs for the LSPs contained in the originating IS's LSDB. All nodes will periodically originate CSNPs to neighbors to ensure LSDBs are up to date. Only the DIS on a broadcast segment, though, will originate CSNPs to the other nodes on the segment. As we mentioned earlier, the DIS will also respond with CSNPs as an acknowledgement for the receipt of LSPs, with those new LSPs included in the new CSNP. Let's now take a look at the bit field format of this PDU. In comparison to the other PDUs, the CSNP is pretty simple. After the common header information, we simply have a length field and then the fields describing LSP IDs. This CSNP can be very long if many LSP IDs are contained. And that's all the information contained in the CSNP. Now let's move on to the last PDU type we'll cover, the PSNP, or Partial Sequence Number PDU. The PSNP is used to request LSPs from a neighboring system. This is done when the LSDB is found to be out of date. An IS will inspect a CSNP and compare it against its own LSDB. If the IS finds that there are LSP IDs listed in the CSNP which are not present in the LSDB, then it will use PSNPs to request those LSPs from the neighboring router. PSNPs are multicasted at layer 2 towards the originator of the CSNP that the local router found had LSP IDs which were not contained in its own LSDB. Let's take a look at this bit field format to see how the PSNP requests specific LSPs. After the common header fields, the key field that the PSNP uses to request LSPs is the TLV fields at the bottom. These will contain LSP IDs for each LSP that the device is requesting. So the receiver can package them up and transmit them to bring the requester's LSDB up to date. And that's it. These are the only 4 PDU types used in ISIS. I appreciate you reviewing them with me. I hope that this lesson has been informative for you, and I would like to thank you for viewing.